This is a quick introduction to the technology behind digital circuits. Okay, so digital circuits basically work with digital signals. Digital signals have a discrete number of values and typically change only at discrete times. And so this can be described as a sequence of numbers. Okay? But normally it's easier to handle them if these digital signals, instead of having multiple values, more than two values, they are restricted to be binary digital signals, only two values. And it can be done very easily because any sequence of numbers can be represented with a set of binary values that we call bits. So 3 can be represented by 1, 0, 1 can be represented by 0, 1. So a digital signal like this can be represented by two digital signals that use the binary representation, or even we can take this binary representation and make a new single digital signal but takes two different values in any period. So it's a signal that carries 2 bits in every period, making the doubling the or reducing to the half the interval. Okay, so number 3 in this interval could be represented by 1 and 0, and it can be represented by half the time the signal is 1, half the time the signal is 0. So when we talk about digital signals, it doesn't make much of a difference if we use multiple values or simply two values. In modern digital circuits, we mostly use, most of the time, binary digital signals. Okay, that's why digital circuits are so much related to the ones and the zeros, representing the two possible values of the signal. So digital circuits basically work with this type of signals. The inputs are things, signals, electrical signals that have a low or high value, and the circuit will generate signals that have only low and high values defined in some way. The way we define those values is based on what we call the logic levels. Okay, a digital signal can be in two values. The logic level 0 is normally associated to a low voltage value, like something close to 0 volts, and the logic 1 digital value is normally associated to a high voltage value, like for example a 3.3 volts. Okay, it would be typical in a circuit that uses a 3.3 volt power supply. It's just for convenience, there's nothing that can stop us from doing it the other way around, like assigning a high voltage to the 0 logic value or a low voltage to the high logic value, but most cases it's done like that. Okay, there's some tolerance. It means that high value will be 1. It doesn't have to be exactly 3.3. It can be something around this value, as long as we can distinguish the voltage is high enough to be considered a 1, and the same thing for the 0. As long as the voltage is low enough, we will consider it a 0. And from here on, when we think on digital circuits, we just can think on zeros and ones, and we can forget most of the time that these are actual voltage or electrical values. Okay, now how we can build circuits that do some useful operations with these digital signals, with these ones and zeros. We basically do digital circuits using transistors. Actually, we use transistors to make the basic digital blocks, and with these digital blocks we connect them together to build a digital circuit. And with transistors, we use transistors in a specific way. Basically, for example, if we use field effect transistors, like in the metal oxide semiconductor transistors, which are the most common transistors used in today's electronics, we just use transistors in two modes. We use transistors as if they were switches controlled by an electrical signal. In the cutoff region of an Pmos transistor, basically we have the gate terminal that controls if current can flow through the other two terminals, the drain and the source. And it happens that in this transistor, when the gate to source voltage is close to zero, the transistor is cut off. It doesn't conduct any electricity. When the voltage of the gate is the gate compared to the source is greater than zero, it have to be greater than some threshold level. It's like 0.7 volts, some small amount. Then the transistor gets into the saturation region and it drives electricity very well. Okay, so we use it when we use transistors in this way. We say we are using them in switching mode. We are not interested what happens with the current here itself. We only rely on the fact that the transistor can be cut off and do not conduct electricity at all. And when it's in the saturation region, it conducts electricity very well. We can consider the circuit is connected here. In the MOS technology, we also have the Pmos transistors that work in a similar way, but with exchanged polarities. In this case, is when the gate to source is zero, it's cut off as well. But to make the transistor conduct electricity, the gate to source have to be negative, okay, less than that. It makes a very good opportunity to build circuits that do basic logic operations, that do basic operations with digital signals. For example, the most simple digital circuit is the inverter that takes a value in the input. From the logic point of view, 0 makes the output to be 1 to take the opposite value, and the 1 in the input makes the output to be 0. From the electrical point of view, I want, when a low voltage is applied to the input, I want a high voltage to be generated at the output, and the other way around. It can be done combining two transistors, two MOS transistor, an NMOS and a PMOS, like this one, like in this structure. Okay, this is connected to the voltage supply, this is connected to the ground, so this is 0 volts, and this is some voltage, maybe 3.3 or 5 volts or whatever. And if we analyze this circuit, when the input is 0 volts, what we have is that from the gate of this transistor to the source, we have 0 volts. So this transistor is open. It does not conduct electricity. But from the gate of this transistor to the source is a positive value, the gate is 0 volts, so the voltage from the gate to the source is negative. So this transistor, which is a PMOS, is conducting. Okay, so with 0 volts in the input, well, we have the output connected to the power supply. It will take a high value of the voltage, very, very close to the maximum voltage here. So low voltage gives a high voltage. As logic 0 gives a logic 1. If I connect the input to a high voltage, to the supply voltage, then transistors are commuted. I have a positive voltage here, then this transistor conducts, and because this is VCC as well, the voltage from gate to source, now it's 0, so it's cut off. Now what we have is the output directly connected to ground, to 0 volts. So a high voltage in the input gives a low voltage at the output. Okay. We can use a simulator to simulate this, and we can see that here a high voltage here activates this transistor. Okay, so this is connected to ground, which is the dark color here, and the output is low. If we switch the input, make it low, now what we do is that we connect this transistor. This is cut off. So we make a connection from high voltage to the output, and the output becomes high, right? In the same way, we can make other logic operations. We normally design circuits to make logic operations that are useful to do complex calculations, more complex logic calculations. So we additionally to the inverter, to the inverting gate, we design other logic gates, which are basic digital devices to operate with two digital signals, like the AND gate that behaves like this one. When the AND gate so only when the two inputs are a 1, only when the two inputs are at the high level, it will give an output at the higher level. Okay, only 1 1 will give 1. Any other combination will make the output to be at the low voltage level. The name becomes from the relation. If we associate the 1 with true and the 0 with false, it means that the output will be true only when X and Y are true. Okay, the terminology is derived from the logic, from the logic area of mathematics. Okay, so it's easy to remember the operation. We have a version of the AND with inverted output. The sign here means invert the signal. So the NAND is like the AND but with inverted outputs. In this case, only when both inputs are 1, the output will be 0 and will be 1 otherwise. We also have the OR that from this logic interpretation is the gate that the output is 1, is true whenever any input is 1, whenever any input is true, X or Y. So this is the table of operation, or the truth table for this OR gate. We also have the inverted version, and then we have the inverted OR gate or NOR gate, and the same way we define some other useful gates like the exclusive OR, which makes the output to be 1 only when inputs are different, when one or the other are 1 but not both at the same time, and the complemented version. Okay, now we'll see in later units why these particular gates with these particular functions are useful, because they make easy to build digital circuits with these gates. But now, how do we build these gates from the basic electronic devices like we have done with the inverter? So first thing to consider is that in when we use the current technology of using Pmos transistors, the functions that we will generate are naturally inverting. It means that it is easier to implement the inverting versions of the gate. So it's easier to implement a NAND than a NAND gate, or a NOR than an OR gate. Okay, so for example, if we want to implement a NAND gate, we can do the same as we did with the inverter, but this time we use two Pmos transistors in series, so that to make the output low, to have a low voltage at the output, I have to connect this transistor and this transistor. That's why we have the AND concept of the operation. Only when both inputs are high, I will connect both transistors, okay? And the output then will be connected to ground. Two high levels will give a 0, which is what tells the NAND operator. The high part here will do the opposite, okay? If any of the inputs is in a low voltage, some of these transistors will be cut off, but some of these transistors, one or the other, will connect the output to the high voltage. We can simulate this gate as well, and we see what happened. Now both inputs are high. We can change the controls to use numeric representation. Okay, so it's more easy to recognize. The logic value. So when both inputs are 1, both transistors drive current, so the output gets connected to ground. When any of the inputs is 0, then this transistor is cut off, but this transistor is conducting, so I have 1 here. If I cut the other transistor, now this transistor is cut, so current goes now through this transistor here, and I have 1. Okay, so basically we see that we have this NAND functionality. The same thing can be done. Well, here is the same thing can be done with a NOR gate with 4 transistors, and that way we can build these basic blocks that do digital operations, very basic digital operations, out of the available technology we have by using transistors. That's all. Thank you.